I'd like to see if you can construct a fourth degree polynomial that has all of these behaviors at x equals 0. So that at its fourth derivative at 0 is 17, its third derivative at 0 is 13, its second derivative at 0 is 11, its first derivative at 0 is 7, and the function itself at 0 equals 5. So I'd like you to take just a minute or two and see if you can come up with a way to do that. I think you should be able to on your own. And if you're struggling to start, I suggest start at the bottom. Don't start at the top. Start at the bottom. Just to make sure everyone's on the same page, what was your fourth derivative down here that you started with? The fourth derivative of this polynomial that you're going to create. Oh, good. 17. Yes. All right. Just to make sure everyone knows what they're doing here, right? This was 17. So if the fourth derivative was 17, what should our third derivative be?
17x plus 13.
Should be 17x plus 13, right? Everybody agree with that? That way, when we plug in 0, that 17x goes away, and it's just this 13. And our second derivative should have been what? Just integrate that. 17 halves x squared plus 13 x plus 11. Yeah? Agree or no? Okay. And what about the next one? (17 sixths x cubed plus 13 halves x squared plus 11x plus 7. Yeah? And what about the last one here? Should have been our actual function, 17 24ths x to the 4th plus 13 sixths x cubed plus 11 halves x squared plus 7x plus 5. Everyone agree with that? We just sort of worked in reverse, knowing what our fourth derivative needed to be at 0. And so every time I can just integrate and plug in that same constant that I get each time, right? Okay. So do we notice anything particularly interesting? I thought I'd just go to this new page now with this. Do we notice anything particularly interesting about these values here? And I'm going to do this. Anything in particular we notice about these values that we've got here, like these constants, these coefficients in front of our x's? This is x to the 0, right? And this is x to the first. Anything interesting we notice about it? Yeah, okay. I like that. You got some factorial stuff right there, except you're all spelling factorial wrong. It's not factorial, it's factorial with an I in there. But that's okay. So 1, that's 0 factorial. The power and the 0 factorial. And this is the power, and this is 1 factorial, and this is 2 factorial, and this is 3 factorial, and this is 4 factorial. Is there a way that we could write this out in a summation form? How far are we going here? To the 4th term, right? N equals 0, 1, 2, 3, 4. In the denominator, what do we have? Of each of these terms, in the denominator we have n, right? Factorial, don't we? And we also in the numerator have x to the n for each of them. But what are all of these numerators? The 17, the 13, the 11, the 7, and the 5. What are those values? Yeah, they're the slopes, or they're the values of the nth derivative at 0, right? Which are the slopes, right? Slope of the previous one, but we would notate that like this: the nth derivative of p at 0. So effectively, that's what we've done here. Is we've written out the 17, 24 x to the 4th, 13, 6x cubed, 11 halves x squared, 7x over 1, and 5x to the 0 over 1 as a sum from n equals 0 to 4 of the nth derivative at 0 of our polynomial. So the 0th derivative of it being the actual value of the function times x to the n over n factorial. And this idea here, this concept here, is a really nice way for us to find a way to approximate pretty much any function to any degree of accuracy that we want by using the values of its derivative times x to the n over n factorial. And we're gonna sort of investigate why this works with another case that's not just a nice simple polynomial. So what we should be able to do is we should be able to write out a polynomial for any function that we can take the derivative of that should match its behavior by using these first, the 0th function itself, 1st, 2nd, 3rd, and 4th, and 5th, and 6th, and 7th, and as far on as we want to go, those derivatives. So we're going to try and take a look at natural log of 1 plus x and use this same method to make a polynomial to sort of model it. So the first thing we're going to do with that is we're going to need to find the value of the polynomial, or the value of the function at 0, the value of the derivative at 0, the value of the 2nd, 3rd, the 4th derivative, as far on as we want to go. And so since this says we want to do a 4th degree polynomial that should match this behavior, we will do exactly that. We'll do a 4th degree polynomial, which means we need 4 derivatives. And we're going to throw it all in to that same thing we just had, the nth derivative of p at 0 times x to the n over n factorial. And so what is the value of our function at 0? Should be 0, exactly. What's the value of the derivative of this at 0? Well, the derivative is 1 over 1 plus x. And if we were to evaluate that at 0, what do we get? Should just get 1, right? Good. And what about the second derivative? So what's the derivative of 1 over 1 plus x? Using the reciprocal rule, that should be negative 1 over 1 plus x squared. And if we evaluate that at 0, what do we get?
Negative.
Negative 1. And what's the derivative of negative 1 over 1 plus x to the second? Should be the opposite of the derivative of the denominator, which is 2 times 1 plus x over 1 plus x to the fourth, and the 1 plus x's will cancel, so that should be 2 over 1 plus x cubed. And if we evaluate that at x equals 0, what do we get? Should get 2, good. And what's the derivative of 2 over 1 plus x to the third? Well, it should be 2 times the 3 times 1 plus x to the second, which is 6 times 1 plus x to the second over 1 plus x to the sixth, which would make it a 1 plus x to the fourth in the denominator. And if we evaluate that at x equals 0, we ought to get, I forgot my negative sign, we ought to get negative 6. Everybody agree with that? Okay. So what we then should be able to do is we should be able to follow this format and write out a fourth degree polynomial that should model natural log of 1 plus x surrounding x equals 0. So what's the first term? What's it going to be at n equals 0? Should be p of 0, which is 0. Well, 0 times x to the n is 0 over 0 factorial is going to be 0, right? So our first term is 0, which we don't really need to write, but we will just for now. What's our next term going to be? Should be 1 times what? X to the first over 1 factorial. And what should the next one be? Should be minus 1 times x to the first. Sorry, times x to the second. It's our second derivative over 2 factorial. And the next one should be what? Plus 2 times x to the third, because that's our third derivative, over 3 factorial. And then it should be minus 6 x to the fourth over 4 factorial. And if we wanted to, we could simplify this down just a bit, right? What would it look like? It would look like x minus x squared over 2, and then plus x cubed over 3, and then minus x to the fourth over 4. And that would be our polynomial, right? Do you guys agree with that? Here's our natural log of 1 plus x. X minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And around 0, if we zoom in some here, we can see that this is a really good model for natural log of 1 plus x around 0. And the more terms to this that we put, the better of a model it should become. And if we had an infinite number of terms, it would look exactly like the natural log of 1 plus x surrounding 0. Everybody see that? Everybody good with that? Pretty cool. It's just another way for us to be able to model these complicated functions using polynomial functions. Could we write this in a summation form now? Could we say that the natural log of 1 plus x, well, it should equal the sum from n equals what? N equals 0 to infinity of what? What does this series look like inside of here if we were to go out infinitely? It's alternating, right? Positive, negative, positive, negative. If I do -1 to the n, that would be -1 to the 0, which would give me a positive. -1 to the 1 would give me a negative. -1 to the 2 would give me a positive, and so on. So that'll make it alternate. What is my x being raised to each term? My first term is x to the n plus 1. And I'm dividing by n plus 1, right? Next one would be -1 to the first, gives me the negative, x to the 1 plus 1, 2, divided by 2. Then x cubed over 3, and then negative x to the 4th over 4, and so on. Good or no? Okay. So let's, now that we've written out this series itself, we had the sum from n equals 0 to start at 1, 0 to 1, and we had -1 to the n, and we had x to the n plus 1, and we divided it all by n plus 1. Right? And so as we went from, we just did like, what, 5 or 4 terms there. If we put 10 terms on, you can see it's even better. 100 terms on. We'll give it a second here. And we'll note that this looks really good from -1. Oh, didn't mean to do that. To 1, right? And right at 1, it diverges off of here. And we could tell that that was the case because if we were to look at the common ratio between our terms, what's the common ratio between our terms? It's each time it's just this x, right? And so we should be able to note what the interval of convergence for is. So what we call this thing is a 4th order Taylor polynomial for our function natural log of 1 plus x at x equals 0. And so like we just saw, if we were to continue to write it out, the approximation around x equals 0 would get even better. Everything diverging away from x equals 0, everything further away gets worse, and or not gets worse and worse, but is worse than it is at x equals 0. So the closer you are to 0, the better the approximation that this polynomial will give you for natural log of 1 plus x. And the reason why we say that it's the approximation is at x equals 0 is because the values of our function and our derivative that we plugged in were 0. So if I were instead to go and use my original function at 1, and then the derivative at 1, and then the second derivative at 1, the third derivative at 1, and write out that series, that would be the approximation for natural log of 1 plus x at x equals 1. And the larger the polynomial, the more terms I put in, the better approximation I would get surrounding x equals 1 rather than surrounding x equals 0. And we're going to do something like that today also. You could put any number in. If you wanted to, get a better approximation of the natural log of 100, right? Well, then you could just have x be 99. You could put in the first, the value of the function at 99, the first derivative at 99, the second derivative at 99, as many terms as you wanted to get as accurate of an estimate as you could possibly get. Does that make sense? So we call it a Taylor polynomial because we've written out a set number of terms. If we were to write out the entire series, as we did with this notation right here, this we would call a Taylor series. And a Taylor series is just a series that is developed using this method of taking the original function at some value, it doesn't have to be 0, and then the first derivative, and then the second derivative, and then the third derivative, and multiplying them by x to the n over n factorial. So far, good. That's sort of what the definition of a Taylor polynomial and a Taylor series is. So we chose to do a 4th degree Taylor polynomial, which requires us to do 5 terms technically, although our first term was 0 for this one, or a Taylor series where we go infinitely. Everybody good or no? Oh God, no, Nick. This works for any function that has ever existed in the universe. So let's do sine x. Yeah, and this is where things start to get really, actually pretty dang cool. I would have chosen a more colorful word if I didn't know you guys were maybe recording me. That specific one is just from natural log of 1 plus x. But it will work for any polynomial. We'll construct a new one for each polynomial. So we're going to go through, we're going to find the value of the function, the first derivative, the second derivative, the third derivative, and so on at x equals 0. And this time it's going to be for sine x. And then so from there, we'll write out the series, look at the series and say, all right, how can we model this as an infinite series rather than just as a polynomial? And you will be astounded and amazed shortly. Guaranteed. All right, so since we're doing sine, it should be pretty straightforward, right? Sine of 0, that's our first value. What's that?
0.
Okay. The derivative of sine is cosine, so cosine of 0 is
1.
The derivative of cosine is negative sine, so negative sine of 0 is 0 again. Derivative of negative sine should be negative cosine, which should give us negative 1. And then the next one, the derivative of negative cosine should be back to sine, giving us 0. And then cosine, back to 1, negative sine, back to 0, and negative cosine, back to negative 1. Everybody agree with that? Everyone's good there? Okay. So what's the first term, the constant term, in our 7th order Taylor polynomial, or 7th degree Taylor polynomial? It should be the value of the function. No, it is 7th order. So the first one gives us a constant, Adrian. So it's not 8th order, it's 7th order. The first one gives us the constant, and then it's power of 1, power of 2, power of 3, power of 4, power of 5, power of 6, power of 7. That's 8th degree, right? The degree is the highest power on the x, not the number of terms. And in fact, we'll see that this one's only, we're only actually going to end up writing out 4 terms because all these ones that have zeros are going to disappear. So the first term should be the value of the function at 0 times x to the 0, which is why it becomes a constant, over 0 factorial, which we've defined as 1. Right, so that term is 0. The next one should be plus 1 x to the first over 1 factorial. The next term should be plus 0 x to the second over 2 factorial. The next term should be minus 1 x to the third over 3 factorial. We should then get plus 0 x to the fourth over 4 factorial. We should get plus 1x to the fifth over 5 factorial. We should get plus 0x to the sixth over 6 factorial and minus 1x to the seventh over 7 factorial. Everybody feel okay about that? We're just following that same pattern. The Taylor polynomial, the original function at 0, the first derivative at 0, second derivative at 0, third derivative at 0, those are all our coefficients. X to the n, so x to the 0, x to the 1, x to the 2, x to the 3, over n factorial, 0 factorial, 1 factorial, 2 factorial, and so on. Everybody good there? Or no?
Yes.
Okay, perfect. Obviously, this simplifies down quite a bit, right? All the ones that have zeros in them just go away. And we're just left with x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. And so this is our 7th order, our 7th degree Taylor polynomial. That should be a good approximation for sine of x at x equals 0. Now, obviously, we don't need to approximate sine of x at x equals 0. But what it's really doing is it is allowing us to see what the curve sine x looks like close to x equals 0. And this is the part where you will be amazed. So we started with x minus x cubed over 3 factorial, which is x cubed over 6. But already, I mean, you can see that around x equals 0, it does a pretty dang good job of modeling that function, right? Very close to x equals 0. In fact, I mean, even beyond x equals -1 and x equals 1, like most of our intervals of convergence for many of our other functions, like all the way up here till looks like 1.414, right? Where it has this max, right? Where it's got this root 2, max of root 2, or max at root 2 and min at -√2. It sort of starts to skew off. And that's with only the first 2 terms. So then I go in here, x to the fifth over 5 factorial, and it looks even better. And if I put in minus x to the 7th over 7 factorial, it starts to look even better. And now it's already almost good for, you know, pretty much one full entire period of the sine function. And obviously, if I were to zoom in, well, maybe not. I'd have to zoom in pretty darn far to see any divergence between those 2 functions, wouldn't I? Especially right around x equals 0. You should be amazed, Nick. Get ready to be even more amazed. Let's go back and see if we can actually write out the series, because it said to write out the actual series as well. So we should have a sum from n equals 0 to infinity of, okay, so it alternates, right? Each term alternates. So what does that tell us we need to have in here? -1 to the n, good. Okay. Now, what about my x values? The first term that I get is x to the what? x to the first, right? And my first factorial down here is 1 factorial. So we might be tempted to say n plus 1 and n plus 1 factorial. Might you be tempted to do that? Seems like that works for the first term. But then when you go to your next term, when you go to x equals 1, or sorry, n equals 1, we're going to have the negative, which is good, but we're going to have x squared over 2 factorial. Well, we need it to be x cubed over 3 factorial. So how can we fix that problem? Making it 2n plus 1, exactly. And if I make that 2n plus 1 factorial and 2n plus 1, that's going to allow me to, every time I go up, have n go up by 1. So when I go to n equals 1, it's going to skip that even number in there, right? I'm going to end up at x to the third, 2 times 1 plus 1, and 3 factorial. And then when I get to n equals 2, I'm going to skip x to the fourth over 4 factorial, which is good because that one was a 0. And I'm going to get x to the fifth over 5 factorial. And n equals 3 is going to give me x to the 7th over 7 factorial. And n equals 4 will be x to the 9th over 9 factorial. Everybody good there? Makes sense? I hope. All right. So we'd already done this up to 7. So now in order to do this a little bit more, we're going to start at n equals 0. We'll just, let's see, we were at n equals 7, which is 0 to 3. So we'll go right back to that, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, right? So that's what we were looking at. Everybody, yeah, everybody good there? So just jumping one more gets even better. Oh man, now I've messed this up horribly. Okay, let's try this again. Jumping one more makes it even better, right? Like I just said. Jumping another one skews off looking kind of funny, but now it's pretty darn good all the way up to like negative, negative 4-ish to 4-ish. Suppose we put in something like just 10. It models this, I mean, almost exactly for these first, pretty much negative 8 to 8. And then after that, it's atrociously awful, right? Let's say, let's see here. Let's see if you can handle 50 pretty quickly. Gotta let Desmos do its thing. There we go. And now it's modeling it really, really nicely for negative, 35-ish to 35. Let's see if we can do 100. I don't know if I can handle 100. That's not 100. That's because I dropped it to 10 for a second. Yeah, maybe 100 is more than it could handle. Let's try 70. Because you got to think, these calculations are pretty difficult for all of these values on here. Yeah, it's struggling here. I think about 50 or 60 was about the best it could handle in Desmos. But zooming in, I don't know, let's just say around 10, maybe, which isn't really all that close to 0. I mean, I'm zooming in pretty far and I don't see any bit of difference even yet between those two functions at some value out here near 10. Right? I mean, it's almost exactly the same, and that's with only 70 terms. Imagine if you went infinitely. And so this is now the second function that we've been able to model using a series that we would note that it sure appears that the interval of convergence for this series is what? should be infinite, right? Negative infinity to infinity. It should converge for all real numbers. And well, yeah, good enough for now. Should converge for all real numbers. And it does. So what we've done is we've constructed an infinitely long polynomial, so we call it a Taylor series, that will exactly replicate the sine function from negative infinity to infinity, which is pretty cool that we can write out this transcendental function, or that's what a trig function is, a transcendental function, using just a polynomial, an infinite polynomial, but it's still a polynomial. All right, so here's what I'd like you guys to try and do. I'd like to see if you can come up with one for cosine of x. So we're going to do a sixth order Taylor polynomial, and then the Taylor series for cosine x at x equals 0. Good or no? You guys think you can do that? I hope so. And then we'll take a look at it on Desmos once we're done and make sure it worked. All right, give it a shot. I'll give you 3 or 4 minutes, 5 minutes or so, and then we'll take a look and see how you guys did. Ready, go. All right, where did we start? We started with the cosine of 0, which was 1, and then the negative sine of 0, which was 0, and then the negative cosine of 0, which was negative 1, and then the next one was 0, right? And then the next one was 1, and then the next one was 0, and the next one was negative 1, and so on, right? Those things just repeat. And so those are our 7 terms for our 6th order polynomial. And so the first one should have been 1 times x to the 0 over 0 factorial. And just again, I'll remind you, 0 factorial is 1. That's how it's defined. And then the next term would have been plus 0 x to the first over 1 factorial, and then minus 1x squared over 2 factorial, 0x cubed over 3 factorial, 1x to the 4th over 4 factorial, 0x to the 5th over 5 factorial, and minus 1x to the 6th over 6 factorial. And all the 0 terms canceled out, right? And you were just left with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and minus x to the 6th over 6 factorial. Does that look like what you guys got for your 6th order Taylor polynomial?
Yes.
Perfect. And as you wrote it out as a series, you should have said the sum from n equals 0 to infinity of what? First thing would have been it alternates, so negative 1 to the n. And what was your x being raised to? Just 2n, good. We got to skip, that's why it's 2n, right? We go from x to the 0 to x to the 2nd to the 4th to the 6th. So we can't have any odd values. 2n will take care of that. And over that same thing, 2n. And be careful how you write this because I almost just wrote it wrong. 2n factorial. Make sure you put the 2n in parentheses there to indicate that first you're multiplying n by 2 and then you're taking the factorial of it. And with any luck, which 2n? Either of the 2n's, or I guess it's the same reason for both the 2n's. So we have to do 2n because we're going from x to the 0 to x to the 2nd to x to the 4th to x to the 6th. The first, third, fifth terms all cancel out and are zeros. So we have to not get any odd exponents. So doubling n takes care of that. And we just have to make sure we, whether we need to attach a +2 or a -2 or it might have been a +1 like it was for the last one to make them all odd. We just have to make sure that we get these correct first few terms. So if n is 0, x to the 0 still gives me 1, which gives me this term. And then when I plug in n equals 1, I get my next term, which is x squared. So that's why it's 2. Does that make sense? Okay. Cool. No problem. All right, so there is our series. There's our 6th order Taylor polynomial. And if we were to go in and put in cosine x, and let's, all we need to do here is change that 2n plus 1 to a 2n. We can see that it starts mirroring, instead of our sine function, it starts looking like our cosine function. If I put in 40 there, for everything I can see on the screen, it looks pretty much perfect. And obviously, if I zoom out, we'll see where it diverges somewhere around 30 something probably, but maybe if it can handle it. There we go. And if we were able to extend this infinitely, we would see that it was exactly the same. This series is the cosine function when written out in its entirety. Good or no? Amaze your friends and family. They'll be so impressed. All right. So last little thing is that we call a Taylor series that has been generated at x equals 0 a Maclaurin series. Sorry, I was reading Aiden's comment. Is the negative 1 x to the 4th over 4 factorial considered the second term or the 4th term? It's the, yeah, so yeah, it's not a negative, you're right. That's the, well, it's the 3rd term technically. Right, this is the 1st term. Well, I guess, yeah, okay. So if we're starting at n equals 0, I mean, the 1st term of the polynomial is this, but really this is the 0th term of the series. This is the 1st term of the series. This is the 2nd term of the series. This is the 3rd term of the series. Yeah, I mean, so I mean, if we were just looking at it as if it was a polynomial, we'd say, oh yeah, okay, we got a bunch of terms of it. But yeah, so you're right. This is the 0th term, 1st term, 2nd term, 3rd term, and so on. They're numbered by the value of n that you plug in. Does that make sense, Aiden? Yeah. All right. Cool. Yeah. So the last thing that I was going to say is this is our formula, right? F of 0, f prime of 0 times x over the 1 factorial. We didn't write the x to the 0 over 0 factorial. Then f double prime at 0 over 2 factorial times x squared, and so on. F, the nth derivative of f at 0 over n factorial times x to the n, or the sum from n equals 0 or k equals 0, whatever. Same thing of the kth derivative at 0 over k factorial x to the k. We call this a Maclaurin series. It is a specific version of a Taylor series. So a Taylor series can be generated at any x value, whereas a Maclaurin series is a Taylor series specifically at x equals 0. And so oftentimes on the AP test, they will talk about a Maclaurin series, and sometimes people will get confused because they don't recognize this distinction that the Maclaurin series has to be at 0. And so they might say, generate a Taylor series for sine x at x equals pi over 2. Well, that's fine. You can do that. You just go in and do sine at pi over 2, and then derivative of sine at pi over 2, and derivative of that at pi over 2, and so on, following this formula. But they may just say, form a Maclaurin series for sine of 4x, right? Well, some people get tripped up because they forget that a Maclaurin series is a Taylor series that has to be at x equals 0. So that's the only distinction here, is that a Maclaurin series is a Taylor series that must be at x equals 0. Okay. And so it's just another name for it. And if we were to take any number of sums of them, any partial sums of this, that gives us our Taylor polynomial of whatever order for the number of n terms that we have. Good or no? Any questions on anything we've done today?